Assalamu alaikum all. Can you hear my voice? What about others? Can you hear me? Yes, Seher, Reem, Nada, Amal. Okay. So we have started chapter number 10, that is Telecommunications Management Network. We have started it. We have discussed about trunk testing system, and we have seen the conceptual model also. Then we were discussing TMN architecture, where we have seen that there are 3 types of architectures: functional, physical, and informational. So the next is we have to discuss them in detail one by one. So the first one is functional architecture, which is made up of 5 function blocks, as you can see over here. We have operation system function, network element function, that is NEF. We have mediation function, that is MF, workstation function, that is called WSF, and queue adapter function, that is QAF. So each function block contains a set of functions, and there are multiple instances of each function. So for example, there may be many operation systems performing different operational functions in the operation systems function block. So the communication between the function blocks itself is a function, but not a function block defined as TMN data communication function, that is DCF. DCF supports the standard transport protocols. So the TMN operation system function, that is OSF, is implemented in operation system. Operation system such as network transmission OS and traffic measurement OS, which helps in monitoring, management, and control telecommunication networks and services. So network management, both as a manager as well as an agent, is also considered to be an OS, that is operation system. So this will include MIB, that is management information base in internet management, and naming tree in OSI management as a function of OSF, that is functions performed by operation system. Now the TMN NEF is concerned with the managed network elements. Network elements are not part of TMN, but they are supported by TMN. Whenever I say TMN, that is Telecommunication Management Network. So it is not a part of TMN, but it is supported by TMN over the standard interfaces. So we have network elements which include hardware, software, and systems such as hubs, routers, switches, processors, nodes, etc. So the network management agent and the associated MIB, management information base, are part of NEF, and network elements providing information for management such as packets dropped, collision rate, etc. are considered as part of telecommunication management network, that is NEF. Now the next is TMN MS block, which addresses the operations that are performed on the information content which is passing between the network elements and the operation systems. So such operations include filtering, store and forward, protocol conversion, and threshold detection, etc. So a physical entity in which the MF is implemented can be shared between multiple operation systems and network elements. For example, we can think of RMON, that is remote monitoring device, which can monitor a remote LAN on various parameters such as statistics on users, protocols, and packet loss and report the analyzed data on raw data to accounting and performance measurement operation systems. So in this situation, the ARMON device acts as a mediation device performing MS between the network elements on the remote local area network and the operation systems, or we can say the network management systems. Now the TMN WSF provides an interface between human personnel and TMN activities. So more specifically, this function addresses the presentation aspect and the conversion function that converts machine-readable information to human interpretable format in the presentation function, which belongs in one of the other three function blocks, that is OSF, MF, and QAF. So this will cover the presentation functions such as graphical user interface and human-machine interface of workstations. So the communication between the four functional models, that is OSF, WSF, MF, and NEF, is assumed to be standardized, and each function in the function block can be considered as providing a service and the service block providing a set of services. So function blocks are designed to be non-overlapping. Now the next is the physical architecture. So a TMN physical block could be the combination of one or more blocks. For example, an operation system could have its operation function as well as mediation device which does filtering of information. Now here in this figure you can see the physical architecture where we have Q, F, and X TMN interfaces between the physical devices, and they represent the physical implementation of respective telecommunication management network reference points. So the Q3 interface is used between the operating system, between the OS and either an NE or a QA, and the QX interface is shown between MD and QA NE. So an example of this will be an MD being a proxy server which is communicating with legacy systems via the QA interface. So the F interface is implemented to connect a workstation to TMN, and the X interface is between the operation systems belonging to two different telecommunication management network. Yes, Munera, connection. Yeah, because of I think some network issue because of weather. I think there is some network issue. That's why the sound quality is not that good. My voice is with my voice. You can hear my voice. What about others? Can you hear my voice? It comes and go. Okay, maybe because of bad weather, there's some internet connectivity problem. So this session is recorded, and if there's any problem at your end, you can hear the session later on also. So this is recorded. Now the next is information architecture, and here we have information model which is specified by SNMP, and OSI management which deals with the management of network elements, and the TMN information model has been used in specific technology such as ATM and SDH SONET. So we will discuss these technologies inshallah later on in chapter number 12. So the information architecture should transport information reliably across the functional boundaries, and there are two types of communication services between interfaces. The one is called interactive and the other is file oriented. This is the service architecture, where we have business management, service management, network management, element management, and managed network element. Now next, let's discuss the ETOM, which stands for Enhanced Telecom Operations. ETOM is a framework specification and it provides a business process model to the telecommunication industry to define the process end to end. So we have Telemanagement Forum, that is TM Forum, which is a body whose mission is to align technology with real businesses and is the next sequential step in the process of TMN implementation. So an important goal of TM Forum is to automate the end-to-end operations that enable the delivery of information, communication, and entertainment services. And this ETOM, that is Enhanced Telecom Operation, is the framework to accomplish this mission. So you can see in this figure, we have a business processes that are described in a layered hierarchical fashion where process at each level can be broken down into lower level process elements, and ETOM is structured in three broad areas, or we can say level 0 processes, which includes strategy, infrastructure, and product, that is SIP. Then we have operations, that is OPS, and enterprise management, that is EM. Now you can see the next figure, that is figure 10.6, and this figure shows the subset of the layers of ETOM map that are implemented as applications in a typical NMS, that is Network Management System, and alongside a rough correspondence with the more traditional ITU-T, that is International Telecommunications Union telecommunications, which is based on TMN visualization. So while the management functional areas in TMN are referred to as FCAPS, FCAPS stands for fault, configuration, accounting, performance, and security. And they are referred to as FAB, that is fulfillment, assurance, billing in ETOM. So the applications in the box of figure 10.16, this one, are typically implemented as part of NMS product, and 10.17 shows the level 2 processes for level 1 processes of FAB activities in service management and operations, as well as resource management and operations. So each level 2 process element is in turn broken down into final level 3 elements, which is representing a greater level of detail. So with this, chapter number 10 is completed, and now we will start chapter number 11, which is based on network management applications. These are the objectives of this chapter, where we will study about network management and system management. We will see the network management configuration, fault, performance, security, and accounting. And we will see the configuration management, that is service network provisioning, inventory management, then fault management and performance management, which includes performance metrics, data monitoring, problem isolation, and performance statistics. So the management of network information services involves the management of network and system resources. This thing you can see in this figure. This is the network information system, which includes the network elements and the system resources. And OSI, that is Open System Interconnect Model, defines the network management as a 5-layer architecture. So at the highest level of TMN are the functions associated with managing the business, that is business management, you can see over here. So this applies to all the institutions, whether it is a commercial business institution or educational institute or telecommunication service provider or any other organization that uses network systems to manage their businesses. Next, an institution is a business that provides either a product or a service. So in either case, there are service considerations, which we call service management. We have network management and system management. And under network management, we have element management, and under system management, we have resource management. So the TMN deals with the network management or system management, and network management manages the global network by aggregating and correlating the data which is obtained from the element management system. Likewise, the system management aggregates and coordinates the system resources by the acquisition of data from the resource management systems. So the complementary functions of network and system management manage the networked information system, which is composed of network elements and system resources. Now next we have configuration management, which includes network provisioning, inventory management, network topology, and database considerations. We will see them one by one, but first of all, what do we mean by configuration management in network management? It is basically used in the context of discovering the network topology, mapping the network, and setting up the configuration parameters in management agents and management systems. So the first one is network provisioning, which is also called circuit provisioning in the telephone industry, and it is an automated process. So the design of a trunk we have already discussed. It is a logical connection, and a station service circuit is done by application programs which are written in operation systems. So we have planning systems and inventory systems that are integrated with design systems to build a system of systems. So a circuit which is designed for the future automatically derives its turn update from the planning system and it ensures that the components are available in the inventory system. Likewise, when a circuit is to be disconnected, it is coordinated with the planning system and the components are added to the inventory system. Therefore, the design system is made aware of the availability of components for future design. Next, we have inventory management, which is an efficient database system, and it is an essential part of inventory management system. So we have legacy inventory management systems that use hierarchical and scalar-based database systems. So such databases limit the addition of new components or extend the properties of existing components by adding new fields. So these limitations can be removed by using relational database technology. Next, we have network topology. So network management is based on the knowledge of network topology. Network topology, we all know, it is the way in which connections are made. So as a network grows, shrinks, or changes, the network topology needs to be updated automatically, and this is done by the discovery application in network management system. So we have an auto discovery feature that can be done using the broadcast ping on each segment and then following up with further SNMP queries to gather more details on the system. So the more efficient method is to look at the ARP cache in the local router, and the ARP cache table is large and it contains the addresses of all the recently communicated hosts and nodes. So using this table, the subsequent ARP queries could be sent to other routers, and this process is continued until the information is obtained on all IP addresses which are defined by the scope of auto discovery procedure. So a map which shows the network topology is presented by the auto discovery procedure after the addresses of the network entities have been discovered. Now here you can see figure 11.2, which shows LAN physical configuration. This is the physical configuration of a conventional LAN. The router in the figure can be visualized as part of a backbone, and there are two LAN segments which are connected to the router, segment A and segment B. So they are physically connected to two physical ports in the router. That is, there is one port for each segment which is used on the interface card, and they are identified as port A and port B corresponding to segment A and segment B respectively. So both LANs and Ethernet LANs are use hub configuration, and we have two hosts, that is A1 and A2, that are connected to hub 1 on LAN segment A, and two hosts, that is B1 and B2, that are connected to hub 2 on LAN segment B. Now next, this figure 11.3 shows the logical configuration of two LAN segments. The logical configuration is the auto discovery process. It is very similar to the physical configuration. Segment A corresponds to LAN on hub 1 with hosts A1 and A2. It is easy to conceptually visualize this and easy to configure. Now this figure 11.4 shows the physical configuration of two virtual local area networks, VLANs. So we have hosts A1 and A2 that are configured to be on VLAN 1, and we have hosts V1 and V2 that are configured to be on VLAN 2. So although VLAN grouping can be done on different criteria, here we have assumed that this is done on port basis on the switch. So the two ports that are marked as segment A on the switch are grouped as VLAN 1, and the other two ports that are marked as segment B are grouped as VLAN 2. So we have segment A which corresponds to VLAN 1, and we have segment B that corresponds to VLAN 2. So we can see that the VLAN 1 and VLAN 2, they are split across the two physical hubs, that is hub 1 and hub 2. And with the layer 2 bridge network, the VLAN network is efficient. So we have IEEE 802.3 standard that is being established and that is being widely adopted, and this configuration has been deployed more and more along with the backbone network. In this figure, we have a logical configuration of our two VLAN segments. Here we have host A1 and A2, which still belongs to segment A, but they are on different hubs. And likewise, we have host B1 and B2, which belongs to segment B. So we have an auto discovery process that will not detect the physical hubs that are identified, and in many situations the switch will also be transparent as there are no IP addresses which are associated with switch ports. So it will be harder to associate the logical configuration with the physical configuration. So we have seen that the network management task is a complex one because firstly it separates the maps that must be maintained on an ongoing basis as changes to the networks are made, and secondly, when a new component is added and auto discovered by the system, a manual procedure is needed to follow up on the physical configuration. So the next topic is fault management, which is very important because here fault in a network is normally considered, is normally associated with the failure of network components and the subsequent loss of connectivity. So the fault management involves a 5-step process, that is fault detection, fault location, restoration of service, identification of root cause of the problem, and the problem resolution. So the fault should be detected as quickly as possible by the centralized management system, preferably before or at about the same time as when the users notice it. So fault location involves identifying where the problem is located. So fault detection is accomplished using either a polling scheme or by the generation of traps. It is the management agent which is based on information from the network elements sending alarms to network management system. So we have an application program in network management system which generates the ping command periodically and waits for response. So connectivity is declared broken when a preset number of consecutive responses are not received. So the frequency of pinging and the preset number for failure detection may be optimized for balance between the traffic overhead and the rapidity with which failure is to be detected. Then we have fault location and isolation techniques. Fault location uses a simple approach, and it will be to detect all the network components that have failed, and the origin of the problem could then be traced by walking down the topology tree where the problem starts. And therefore, if an interface card on a router has failed, all the managed components connected to that interface will indicate failure. Next, we have performance management. So the performance of a network is hard to define or quantify in terms of global metrics. The purpose of the network is to carry the information, and therefore the performance management is really data traffic management. It involves data monitoring and problem isolation, problem tuning, analysis of statistical data for recognizing the trends, and resource planning. So we have performance metrics. That means the parameters that can be attributed to define the network performance on a global level, which is throughput, response time, network availability, and network reliability. So the metrics on these are dependent on what, when, and where the measurements are made, and the real-time traffic performance metrics are latency, that is the delay, and jitter. Next is data monitoring. This is done in the network for abnormal performance behavior, such as high collision rate in Ethernet local area network, excessive packet drop due to overload, etc., and are detected by traps generated by agents and RMON, that is remote monitoring networks. So thresholds are set for important SNMP parameters in the RMON, which then generate the alarms when the preset threshold is crossed. So for example, the parameters in the alarm group and the event group is set, and for the object identifier to be monitored, and the time interval over which the data to be collected for calculation, and the rising and falling thresholds are specified. So in addition, the community names are set for who will receive the alarm. Next is problem isolation. For performance-related issues depend on the type of problem, and a high percentage of packet loss will cause loss of connectivity, which could be intermittent. So in this situation, monitoring the packet loss over an extended period will isolate the problem. As in fault management, problems could occur at multiple locations simultaneously. So these could be reported to the central management system as multiple independent events, although they may be correlated. So for example, an excessive drop in packets in one of the links may switch the traffic to an alternate route. So this could cause an overload in that link, which will be reported as an alarm. And finally, we have performance statistics, which is used in tuning a network, analyzing the trends, planning the facilities, and functional accounting. So the data is gathered by means of RMON probe and RMON MIB for statistics. Statistics to be accurate require large amount of data sampling, which create overhead traffic on the network, and therefore it impacts its performance. So one of the enormous benefits of using Armon probe for collecting the statistics is that it can be done locally without degrading the overall performance of the network. So one application of the results obtained from performance statistics is to tune the network for better performance. For example, we have two segments of the network that may be connected by a gateway, and excessive inter-segment traffic could produce excessive performance delay. So the error statistics on drop packets on the gateway interfaces will manifest this problem. So various error statistics at different layers are gathered to measure the quality of service and to do performance improvement. Now next we have traffic flow measurement network characterization. Here we have four labels which are defined by IETF. We have three measurement entities, that is the meters gather data and build the table. It reorders the collected data from the meters and the managers oversees the operation. Now here we have some event correlation techniques. There are several correlation techniques which are used to isolate and localize the faults in networks, and all are based on detecting and filtering of events, correlating the observed events to isolate and localize the fault either topologically or functionally, and identifies the cause of the problem. So in all three cases there is intelligence on, or we can say reasoning behind the methods, and the reasoning method distinguishes one technique from another. So we have 6 approaches to correlation techniques. They are rule-based reasoning, model-based reasoning, case-based reasoning, codebook correlation model, state transition graph model, and finite state machine model. So the first one is rule-based reasoning. It is the earliest form of correlation technique. It is also known by many other names such as rule-based expert system or expert system or production system and blackboard system. It has a knowledge base, it has working memory, interface engine, as you can see in this figure. The 3 labels represent the 3 components, and they are the knowledge label, data label, and the control label. So the knowledge base contains the expert knowledge for the definition of a problem in the network and the action that needs to be taken if a particular condition occurs. So the knowledge base information is rule based in the form of if then or condition action containing rules that indicate which operations are to be performed and when. So here you can see the basic rule-based reasoning paradigm. This is an interactive between the 3 components and is iterative. And there are several strategies for the rule-based paradigm. We have a specific strategy which is implemented in the inference engine. Choosing a specific rule, an action is performed on the working memory element, which could then initiate another event. So this process continues until the correct state is achieved in the working memory. And we have rules that are made up in the knowledge base. from the expertise of the experts in the field, and the rule is an exact match and the action is very specific. So in the rule, if the rule does not match, the paradigm breaks and is called brittle, and it can be fixed by adding more rules, which will increase the database size and it degrades the performance. So this is known as knowledge acquisition bottleneck. This is the rule-based reasoning. Some of the rules are stated over here. Now in this figure, we have RBR based correlation example scenario. It shows a 4-layer network. The backbone router A links to router B. Hub C connected to router B has 4 servers, that is D1 through D4 in its LAN, and without a correlation engine, failure in the interface of router A will generate an alarm. So this fault then propagates to router B, hub C, and finally to servers D1 through D4. So it is important to realize that there is a time delay which is involved in the generation of alarms. And in general, the propagation of faults and time delay associated with them need to be recognized as such in fault management. Now you can see in figure 11.11.11, where we have model-based reasoning. The right half shows the corresponding model in the event correlator in the network management system. The NMS pings every hub and the router periodically to check whether each component is working or not. So we can associate the communication between the network management system and a managed component as between a model. So this is our example. The model of each hub periodically pings its hub and the model of the router pings the router. So as long as all the components are working and no additional operation is needed. Now, if hub 1 fails, then it is recognized by H1 model. And let us assume that H1 model is programmed to wait for lack of response in 3 consecutive pings. So after 3 pings with no response, the H1 model suspects a failure of hub 1. However, before it declares a failure and displays an alarm, it analyzes its relation to other models and it recognizes that it should query the router model. So if the router model responds that the router is working, only then hub 1 alarm is triggered. And if the router model responds that it is not receiving a response from the router, then hub 1 model deduces that the problem is with the router and not with hub 1. So at least it cannot definitively determine a hub 1 failure as long as it cannot communicate with hub 1 because of the router failure. So this is all. Rest of the topics you have to cover yourself, and if you have any question you can ask in face-to-face lecture or in upcoming virtual lectures, or you can mail me anytime if you have any problem. This is all. If you have any question you can ask. No query? Okay then. We will meet in next face-to-face lecture then. Till then, take care all of you. Assalamu alaikum.